this is again our quantum computer. Now we have to agree about the qubits encoded in it. And we decided the first qubit to be the path in the interferometer. So let it be 1, the left path, and 0, the right path. And the polarization is the second photon. Let it be vertical polarization to be 1, and horizontal polarization to be 0. And if our polarizer here is oriented like this, then on the input at this point we have this state. And after the first beam splitter, we will have this state. And we are now ready to apply the quantum oracle, because Hadamard transforms are already applied by this polarizer and beam splitter. So I told you that I'm going to implement the quantum oracle by these wave plates. And the wave plates I'm going to orient like this, orthogonal to the photon's polarization. So the action of a wave plate will be multiplication of the state we have by -1. Now we have 4 different quantum oracles, which may situate in our interferometer. And the first one is, you remember, identity here, which means nothing happens to photons, and we don't place any of wave plates here. Now the second is this, which applies X gate to the second photon independently of on the value of the first photon, which means we have to multiply our state by -1 on both ways. So the polarization must change independently of the path, and we put wave plates on both paths. Well, the next situation is for f of x equals to x. And we have to multiply the state by -1 only if vector x is 1. So it's the left path of interferometer. Here we have the first qubit equal to 1, and we place the wave plate here. So for this qubit, we have multiplication by -1, and for this vector, we don't. And vice versa. For this case, we have to multiply the state by -1, the vector by -1, only if our first qubit is 0, which is the right path. So we place the wave plate on the right path. So with these wave plates, we can entangle the position of the photon with its polarization. And we can implement all 4 quantum operators, quantum oracles, we need for solving the Deutsch problem. Now, imagine that we have some configuration of these wave plates here, and then someone comes and covers all this with some black cloth, so we can see what configuration we have. Can we still decide if the function implemented here is a constant or a balanced function? Yes, I told you about the interference. So the photon goes by two paths and it presents the interferential pattern here and here also. Let's imagine this interference pattern with no wave plates inside the interferometer. So it's going to be something like this. We have, with red, I draw maximus of interference picture. So here both photons come with their maximum and it adds up, and the black places are here, which this photon comes, the points where the photon comes in contraphase. Okay, we have this interference, and what if we put the wave plates on the both ways, on the both paths of the photon? Will the interference picture change? It will not, because the difference of the path does not change. The photon experiences a delay on the both paths, so this white and black, red and black spots will stay on the same place. And now if we put a wave plate only on one path and the other is free, then the points where the photons came both with their maximas, one photon still comes with its maxima, which goes free, and the second photon is delayed by half of its wavelength, so it comes here with its minima. And on the red points here, we will have, in this case, the black points. And instead of black points, we will have red, so the interference pattern will shift. And this is how we can distinguish the difference between the constant function and a balanced function. And this is what we have, the balanced function here. So the wave plate on one path, here on the right and here on the left path. And we see that the interference pattern is the same for both configurations. And for these type of configurations, with either the wave plates on both ways or no wave plates, we have this shift of bands. So we can see here, marked with a pen, the lighted shift, the lighted band, and the black bands between these lighted bands. And when we change the configuration of interferometer, these traces of pen now are on the dark places of the interference picture. Of course, if we tuned our interferometer better, we would have not these bands, but rings, as I draw in the previous slide. And with a well-tuned interferometer, these rings are much thicker. But this kind of tuning is really hard to achieve on this interferometer made on handmade interferometer made on chip board. So still, we have implemented a real quantum algorithm on a real quantum computer. Let's go further.